Hi everyone, welcome back. In this segment, we will continue with integration topics related to integration, such as finding the average value of a function. That is an application of integration. And then we'll also take a look at some general things like properties of integrals, the second fundamental theorem of calculus, and also the net change theorem. So they're a little bit like, a few different topics all put together, but they all have one thing in common. They're all about integration, okay? So let's begin with average value of a function. So average value of a function is an application of integration. And here is what the formula looks like. 1 over b minus a times the integral from a to b f of x dx. So this would give you the average value of f of x over the interval from a to b. So basically you take the integral of f of x over that region and you divide it by the length of the interval. That's what 1 over b minus a represents. Now, just to give you an intuitive explanation of this formula, let's take a look at a function that is a constant function. F of x equals c. So it's a constant everywhere, okay? So if you were to find the average value of this function over this interval, you would say, okay, it's a constant, so the average value should be the constant. So basically, we're finding the average height of the function. For a constant function, the average height will be whatever that constant is, right? If this was a 5, the average value this function attains over that interval is 5. Now, let's apply the formula to see if that will really give us what we expect, okay? So the average value of a function formula says, take 1 over b minus a. So if the interval is from a to b, you're dividing it by the length of the interval, b minus a. And then you integrate the function being the function c, over the interval from a to b with respect to x. Now, what is the antiderivative of c? What is the antiderivative of c? So that's c times x, right? C times x. So that's one way to look at it. You would say c times x and then plug in upper limit minus lower limit. But the other way to look at it is, since this is a positive function, this will give you the area of that rectangle. And the area of that rectangle is base times height. The height is c units. The base is b minus a units. So therefore, the integral of a to b of c dx is the same thing as c times b minus a. That's the area of your rectangle bounded by the function, okay? So c times b minus a. And at this point, the b minus a's will cancel and you would really get c as the final answer. So for a constant function, at least, it's very easy to check that the formula is really working because the formula takes basically, in a way, the area under the function and it divides it by the length of the interval, and that returns basically the average height attained by that function. And this formula applies both to positive and negative functions, and you don't have to split into intervals or anything. You can just directly integrate from a to b, whether the function is positive or negative. So if sometimes it's negative, average height can be negative. That's fine. Okay, so let's take a look at this example. Find the average value of x cubed plus 1 over the interval from 1 to 3. So we're going to apply the rule that we just learned for the average value of a function. 1 over b minus a will be 1 over 3 minus 1, or 1/2, times the integral from 1 to 3 of x cubed plus 1 dx. All right, so let's integrate the function. So you have 1 over 2 that was in front. Keep that in front still. So you're going to have x to the 4 over 4 plus x evaluated from 1 to 3. At this point, plug in the 3 for x. Everywhere you see an x, plug in a 3. And this 1/2, you can keep it outside of everything. So after the 1/2, I open a parenthesis, and first I'm going to plug in the upper limit. You're going to have 3 to the 4 over 4 plus 3. So 3 to the 4 is 81, so 81 over 4 plus 3, minus, open another set of parentheses. This time put in the lower limit, which will be 1 over 4 plus 1 inside the parenthesis. And at this point, you can distribute the negative sign and simplify. So you're going to have negative 1/4 minus 1, and don't forget the 1/2 is out on the outside of everything. Let me do that over here. I have a shortcut there. So we have 1 over 2 on the outside of everything. Then inside the brackets, we have 81 over 4 minus 1 over 4. That's 80 over 4. and then I have plus 3 minus 1. Notice I'm putting together the ones that are fractions together and the ones that are whole numbers together, and then I'm going to combine them. So 80 over 4 is 20, 3 minus 1 is 2, so I have 22 basically. So I'm getting 1 over 2 times 22, and that gives us our final answer of 11. So we're getting that the average value of this function over the given interval is 11. So basically you're finding the average height of the function. And if you think of this, say, you know, there's a stock, sometimes it's positive, sometimes it's negative, and you may want to know over time, what is the average value of the stock over time? If you happen to know the equation that represents the value of the stock, all you have to do is integrate it over the given interval and divide by the length of the interval. That will give you the average value of the function. All right, let's do one more example. Find the average value of f of x equals 6x squared minus 4x plus 1 over the interval from -1 to 1. So this would be a perfect example for you to try first and then come and join us. Okay, so I'll be going over the solution. Hopefully you already tried it. One thing to pay attention to here is the interval goes from -1 to 1. So when you're doing 1 over b minus a, it's going to look like 1 over 1 minus -1. So it's going to be actually 1 over 2. Indeed, the length of that interval is 2 units. So that should make sense that we're going to divide by the length of the interval. So divide by 2 basically. Okay, so finding the average value. 1 over 2 times the integral from -1 to 1 of our function, 6x squared minus 4x plus 1. And let's take the entire derivative of the function, 6x to the 3 over 3, that's 2x to the third, minus 4x squared over 2, that's minus 2x squared. And the integral of 1 is just x, going from -1 to 1. And now all we have to do is plug in the upper limit minus plug in the lower limit. I would leave the 1/2 on the outside of everything and only distribute that in at the end. So I would open a set of parentheses and enter the positive 1 everywhere you see an x. You're going to get 2 minus 2 plus 1. And then minus, open another set of parentheses and plug in -1 for x. You're going to get -2 minus 2 minus 1. And at that point, you could simplify each quantity within the parenthesis and then subtract. There's a number of ways you can go about it. So for example, 2 minus 2 is 0, plus 1 is 1. So over here I have a 1. All right, 1. And then on the second set of parentheses, I have -2 minuses minus 4 minus 1. That's minus 5. So what we really have right now is 1 over 2 times quantity 1 minus -5. So that's 1 over 2 times 1 plus 5, or 6. So our final answer appears to be 6 over 2, or 3. So 6 over 2 is our final answer. Okay, so average value is not a difficult concept. Just be careful, with your signs. Make sure you can set up the formula correctly. And remember, you don't have to split these over intervals. Just whatever the given interval is, you go from there to there. You don't have to look at it as positive or negative in the intermediate values between the given points. All right, so next we're going to take a look at properties of integrals. And we've already used some of these properties really, but this kind of puts everything on the same page, giving us a chance to review all the properties of integrals at once. Property number 1, integral from a to a, from the same number to the same number, like from 3 to 3, f of x dx. Any guesses? If you said 0, you were correct, because basically think of it as there's no area whatsoever. We're standing still at the same point, right? You can also think of this as entire derivative of capital F at a minus entire derivative capital F at a. When you subtract, the difference is 0. Okay, what about the integral from a to b of f of x dx versus the integral from b to a f of x dx? What's the relationship? One is -1 times the other. Okay, so if you switch the order of integration limits, then you end up with -1 times the previous answer. Again, there's an easy explanation because this one will be the one on the left, capital F of b minus f of a. The one on the right, without the negative sign, would have been capital F of a minus f of b. But once you put the negative sign in front, they are equal. Okay, property number 3. So if you're going from a to b and then b to c of f of x dx for a continuous function, then that will be the same as going from integral from a to c. Okay. It's similar to this situation here. You have a function, a continuous function. You're going from a to b and then from b to c. So that's as if you're going from a to c of the integral. All right, here's another property of integration. If you have a constant multiple, we talked about this before, you can take the constant outside. And then the last property we're looking at is, actually there's one more, sorry. Property number 5. If you have a sum or difference, you can distribute the integral sign over the sum or difference. This is because integration has very similar properties as summation, because after all, you know, it's really simplifying a process that summation, sigma notation, was doing. So it has similar properties, such as take out a constant, such as distribute over a sum or difference. And then the last one is the integral from a to b of just a constant, and that will be c times the length of the interval, c times b minus a. And again, if you want to see a visualization of this, say your function c is a constant function and you're integrating it from a to b. So finding the integral from a to b of that constant is the same as finding the area of that rectangle bounded by the line y equals c from the point A to the point B. So it's basically going to be the length times the width, which is b minus a, times the height, which is c. Okay, with these properties, we can do all sorts of examples. All right, so let's take a look at this one. The integral from 5 to 5 of x squared plus 3. That one should be easy, right? You're standing still in a sense. There's nothing to add. It's just going to be 0. Okay, what if you know the integral from 2 to 3 of the function is 10? What do you think that will be the integral from 3 to 2 of the same function? If you said negative 10, you are correct. We're using properties from the previous page. What about this example? Integral from 2 to 5 f of x dx is 12. From 3 to 5 f of x dx is 8. And what about integral? What will be the value of the integral from 2 to 3 of f of x dx? For this question, take a moment, please. Pause the video here. So something to remember is integral from 2 to 3 plus 3 to 5. So if you're going from 2 to 3 and then 3 to 5, that will give you, that's the same as the integral from 2 to 5, right? So let's set up an equation. So integral 2 to 5 equals integral from 2 to 3 plus integral from 3 to 5. So let's put in what we know. We know this side is 12 and 3 to 5 is 8. The unknown is this quantity over here, integral from 2 to 3, right? So if you set up a very simple equation, you're going to see that 12 equals the unknown plus 8. So the unknown quantity, which is the integral from 2 to 3, will be 12 minus 8, or 4. Okay, another example using properties of integration is right here. You're asked to find the integral from 3 to 8 of 2 times f of x plus 5 dx. Excuse me, this one is actually given. This is given as 24. What we are asked to find is the integral from 3 to 8, just f of x dx. So can you use this information to find the integral from 3 to 8 of just f of x dx? So let's kind of dissect the one on the left-hand side a little bit. Like, how can we use properties of integration to simplify this as much as possible? So first of all, I can distribute the integration over the first plus over the second, right? And then I can factor out the constant multiple. So I can rewrite that as 2 times integral from 3 to 8 of f of x plus, distributing it to the second term, integral of 5 over the same limits equals to 24. That's the given information. And we're supposed to find integral from 3 to 8 of f of x, right? So basically, this is the part we want to solve for. So do we know this one? What is the integral of 3 to 5 of 5 dx? Since that's just a constant, take the length of the interval, 8 minus 3 is 5, multiplied by the constant function of 5. That was one of the properties we saw on the last page. So that will be 25, right? Now subtract 25 from 24. So if you subtract 25, remember this is 25. So 24 minus 25, that's -1. So that means this quantity, integral 3/8 of f of x dx times 2 is equal to -1, which is 24 minus 25. Okay, at this point, how do you find the integral from 3 to 8? Just divide both sides by 2, and you're going to get -1/2 for the answer. So we had to kind of manipulate the left-hand side using properties of integral and to isolate what was being asked of us, which was integral from 3 to 8 of f of x. So the answer is -1/2. Okay, one last example using properties of integration. Let's say you know the integral from 1 to 3 f of x dx is 5, and also integral from 1 to 3 g of x dx is 6. Could you figure out the integral from 1 to 3 of 2 times f of x plus 4 times g of x dx? Again, this will be a great problem for you to try first and come back and check your answer. So hopefully you're coming back to check your answer. First, distribute your integral sign over the first term plus over the second term. In each case, you can factor out the constant multiple. So you will have 2 times the integral of f of x dx from 1 to 3 plus 4 times the integral of g of x dx from 1 to 3. And we are given the values of f of x from 1 to 3. That integral was 5. So you can put a 5 for this segment over here. And the integral of g of x from 1 to 3 was 6. So you can put a 6 over here. Don't forget to multiply those values by the numbers preceding them. So you're going to have 2 times this integral, which was 5. So you're going to have 2 times 5 plus 4 times this integral, which is 6. So plus 4 times 6. So we have 10 plus 24, or 34 for the final answer. So these questions are relatively easy if you're familiar with the properties of integrals. All right, and the last item on the agenda today is, actually we have 2 more items, sorry. Second fundamental theorem of calculus. I'm going to spend very little bit of time here. This one doesn't get as much use. Just for those of you who are going to move on to higher levels of math, I just want you to have a little bit exposure in this. So just simply speaking, if you have the derivative of an integral, they cancel each other, and you're going to end up with what was inside evaluated at this upper quantity x. And for this to work, the lower limit is always just a constant. So for example, if I have the derivative of the integral 5 to x of 3t squared dt, say I didn't even know this theorem, what would I do? I would take an antiderivative of 3t squared, which would be 3t to the so the antiderivative is 3t to the 3 over 3. But don't forget there's a derivative up front, and now you're going from 5 to x. Plug in x for t. Of course, the 3's cancel. You're going to have x to the third minus plug in 5 for t. You're going to get 5 to the third, or 125. So now differentiate everything. Derivative of x cubed is 3x squared, and derivative of the constant is 0. So what you're going to end up getting is 3x squared. What would have been the easier approach? Using the fundamental theorem, which is the second fundamental theorem, which says derivative of an integral, they're going to cancel each other. Just take what's on the inside and evaluate it at that upper value of x, and there you have the answer. Notice it's the same exact answer. Here we did the long about way, first take the entire derivative, then take the derivative. Here we're just applying the result as mentioned over there. So for example, for this one right here, the derivative of the integral from 4 to x of the square root of 4 plus t squared. Well, this one is not an easy integral, so we couldn't even do this second approach we did over there. Let's just apply the fundamental theorem. It says derivative of an integral, they're going to cancel each other, and just replace the t with x. So the answer will be the square root of 4 plus x squared. Again, it's a relatively low usage theorem in mathematics, but yet it might be important in the future, so I just didn't want you to miss on it. So at least now you know what the second fundamental theorem is. And drum roll please, the last item is the net change theorem. Let's take a look at that one. So the net change theorem is, in a sense, repeating something we already know, but you can do some very interesting questions, application questions with it. So what it's saying is, if you take the integral of the rate of change of something, the integral of g prime of t, for instance, then if you take the entire derivative of g prime, you get g, right, the function g, and you plug in the upper limit, you get g of b minus g of a. So this is very much like the first fundamental theorem, but it's put in a different way. It's saying when you take the integral of a rate of change function, you're going to find the total change in the original function over the given interval. Okay. So for example, a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute, where t is between 0 and 60 minutes. Find the amount of chemical that flows into the tank during the first 20 minutes. So this is a typical application of the net change theorem. You know the rate of change of something in liters per minute. And you're going to integrate it over the given region from 0 to 20 to find the total amount of liquid or chemical that flew into the container during that time period. So just take the integral of the rate of change function, which is 180 plus 3t, over the interval from 0 to 20. And if you analyze the units, 180 plus 3t units for that, that's the rate of change of a chemical, so that's liters per minute. And dt, think of that as time, right? Say minutes. And if these, they're being multiplied, so the minutes cancel. The end result will be liters. So when you integrate the rate of change with respect to time, you're actually going to find the total number of liters that accumulated in that container over that given period of time. So, and the integrals are usually going to be relatively simple ones, like integral of 180 is 180t, integral of 3t is 3t squared over 2, and limits are going to be from 0 to 20. So take a moment to plug those in and come back to check your answers. So plugging in for 20 for t, and when you plug in 0, you get nothing, right? If you simplify all of that, you will have 4,200 liters. All right, a couple more examples. All right, at 1 p.m., oil begins leaking from a tank at a rate of 4 plus 0.75 t gallons per hour, where t is the number of hours since 1 p.m. How much oil is lost from 1 to 4 p.m.? So here t is defined as number of hours since 1 p.m. So at 1 p.m. t will be what? If you said 0, you are correct. At 4 p.m. t will be 3, right? 3 hours have elapsed over that time. So because of the way t is defined in this case, it's number of hours since 1 p.m. So we have to subtract 1 from each number to get the actual value for t. And then the function we're integrating is going to be the rate of change function. 4 plus 0.75 t is the function we're integrating. So the rate of change of the oil in the container is this. When you integrate it over 0 to 3, you're going to find out how much oil is lost over that time period. And so integrate it to get 4t minus 0.75 t squared over 2 over the given limits. And take your time to plug the values in and come back to check your results. And you should get 15.4 roughly gallons. This one was gallons, last one was liters. And what about how much oil is lost from 4 p.m. to 7 p.m.? Again, remembering t is the number of hours from 1 p.m. So subtract 1 from each of these. So when t equals 3 to t equals to 6. So we need to integrate this from 3 to 6. Same exact problem, but integrated from 3 to 6. And please do it. And I'll show you the final answer there for you to check later on. 22.1 gallons. Okay, so we're just plugging a 6 everywhere we see a t, and then we're plugging a 3 everywhere we see a t, and don't forget subtraction sign in the middle, and then we just simplify. One last example on the net change theorem. So here we go. A car is traveling at a rate of 44 feet per second, it starts decelerating at 3 feet per second square until it comes to a complete stop. How long did the car travel from the moment it started decelerating? So this was quite a bit more complex than the last two. So let's try to analyze it a little bit. So it was going at 44 feet per second when its person maybe start pressing on the brakes, and they're getting slower and slower at a rate of, basically they're slowing down by 3 feet per second every second, right? So you could say the velocity is equal to 44 minus 3t, because after 1 second it's going to be 41. After 2 seconds, it's going to be like 44 minus 6 and so forth. So after each passing second, it's slowing down further. That's what decelerating by 3 feet per second square means. So we have an equation for velocity. It started at 44 at time equals 0, but it's slowing down over time. Next thing we need to figure out is, when does it come to a complete stop? Because ultimately they want to know, how long did the car travel from the moment it started decelerating? So to know the limits of integration, if you call t equals 0 the moment it started decelerating, you would need to know what is the upper limit of integration. When does it come to a complete stop, right? How do you think we could find that? How do you think we could find the moment when it comes to a complete stop, if this is your velocity equation? If you said set velocity equal to 0, you are absolutely correct. So set velocity equal to 0 to see how many seconds will it take for this object to come to a complete stop. And so you're going to add 3t to both sides, multiply by 3, you get 44 over 3, which is roughly 14.67 seconds. Okay, to find the total distance the car traveled, we're going to integrate the velocity function, because remember, velocity is the rate of change of distance, right? So if you integrate velocity, you're integrating s prime. So the entire derivative is s, right? So it'll be s of b minus s of a. So you're going to find the total distance traveled between the time equals a to time equals to b. So integrating velocity gives us distance. So again, you're in a sense integrating the rate of change to find total change in the distance function. So we're going to integrate 44 minus 3t. Okay, that's what I already mentioned to you. So integrate the function 44 minus 3t over the given interval 0 to 14.67, and the antiderivative is 44t minus 3t squared over 2. And plug in the limits. You plug in the upper limit minus the lower limit, and please do this on the calculator and check your answer here. The final answer turns out to be 322.67 feet. That's total how far this car has traveled from the moment it pressed on the brakes. Okay. All right, so that concludes the section. I know there was a lot of different things in here, all connected with the one general topic of integration. And so I hope you can go back and do lots of practice questions about everything we've covered here, anything from average value to properties of integrals to the net change theorem. Have a great day, everyone.